So in the time remaining and after the lab, we're going to review material for exam. That says exam 6. It's exam 5. Okay. This is a legacy review document. It's holdover from a previous semester where we did have exam 6. This one we're taking, but it's on chapter 16. So that should be exam 5 for us. All right, so let's start with number 5. Move these guys up here, down here. All right. So barium carbonate has a measured solubility. Barium carbonate. Barium carbonate. Remember, this is the alkaline earth. This is the polyatomic ion. Right. So we just need one of each. That's the formula for barium carbonate. You got to know that in order to write this equation. So this is the equation we're basing our work off of. I just ended a sentence with a preposition. An English teacher's rolling over in her grave. Okay. The solubility is measured at 4.03 times 10 to the minus 5. Molar. What we want to know the KSP. So the KSP would be just the barium. Since its coefficient is 1, it's to the first power, and carbonate to the first power also. So what we need are values that can go in here to give us that. Okay, so I set up an ice table. If the solubility is a value of S here, that means that for every one of these that goes into solution, you get one of those, right? So initially we got nothing. And then we get a change of a plus S and a plus S. Okay, so at equilibrium, we have S and S. That simply means, and this is as simple as it gets, that simply means that that S is this S. So what we have here is 4.03 times 10 to the minus 5 squared, because it's 1 here and 1 here, times 2 squared. So you just have to square that value, and that will give you the KSP for this compound. Now I get 3 significant figures. So the KSP is going to be 1.62 times 10 to the minus 9. That's E. Okay. We're starting off simple. All right, that was 5. And 6. Okay. The correct mathematical expression for finding the molar solubility of, excuse me, 10,2 hydroxide. All right, so it's going to break up into that and 2 of these. Okay, aqueous. So we're looking for the general expression for finding the solubility if we know the KSP. Right. So the KSP expression is going to be 10, 2 plus, and OH minus squared. So we need values for these guys right here. Well, if we know the molar solubility here, and the initial is 0, then the change is going to be, for every one of these, you get one of these. And for every one of these, you get 2 of these. Right? So at equilibrium, you have those values. So we plug those in here because this is equilibrium. Okay? So we get S, and here we get 2S, and this term is squared. And so S squared times S is S cubed, and this is 4S cubed. Okay. Alrighty. Let's see. Number 11. Which of the following compounds has the lowest solubility in molarity in water? One thing that's, we can't use the trick here, but if every compound that you're comparing gives you the same number of ions in solution, or it's the same, it's the same overall form, like if you've got X and Y, say 3 of these and 1 of those, or if you've got 3 of these and 2 of those, something like that. If they're all the same, then you can compare directly the KSPs and determine which one is more soluble. But in this case, they're different. Some of them are alike and some of them are, the rest of them are different. So we have to actually calculate the solubilities for each one. All right, so this is going to take some time, but if you use Henry Ford, it shouldn't be too traumatic. Through E? Yeah. Okay, so silver phosphate, like that. And then we have the one we just finished, and cadmium sulfide. Okay, and we have calcium sulfate and aluminum hydroxide. Okay. If we okay. I just had to think for a second. We're gonna do the same operation on each one of these. So this one's going to produce 3 silvers. I'm going to leave off the aqueous part in the interest of time. Then we have the tin, we have the 2 hydroxyls, and we have the cadmium, and it's 2 pluses. This is 2 pluses, and the sulfur is 2 minuses, and then the calcium is 2 pluses, and the sulfate is 2 minuses. The aluminum is 3 pluses, and the hydroxyls. So let's see. That looks good. Okay, so the KSP expressions for each one of these would be, well, let's look at it this way. If the solubilities, if we start with solubilities for each one of these, then what does that give us for each one of these? Right. This is going to be 3 S's, right? This is going to be 1 S. Okay. This is going to be 1 S here. This is going to be 2 S's there. This is going to be an S and an S. This is going to be an S and an S. And this is going to be an S and a 3s. Okay. Now, when we write the expression, 1.8 times 10 to the minus 18. That will be this one times this one, but this one's to the third power. So this will be s, and then 3s to the third power. Okay, see the pattern is developing. 3 times 10 to the minus 27. And this is going to be an s and a 2s squared. This is going to be 10 minus 28. 1, 1.0. Times 10 to the minus 28. This is going to be just an s and an s. Okay, same thing for this one, but it'll have a different KSP. 6.1 times 10 to the minus 5. And this is an s and an s. And the last one is 10 to the minus 33. So 2.0, not just 2. 10 to the minus 33. And this is going to be an s and a 3s cubed. Okay. So now all we have to do is solve for each one of the s's. Right. So this term here is going to be 3 times 3 times 3 is 27, s to the 4th. Okay. This one's going to be, well, we did this one before. This one should be 4s cubed. This one's going to be s squared. This will be s squared. And this will be same as that one. 27 s to the 4th. Okay. So in order to find out what s is, the solubility, we'll divide this one by 27 and take the 4th root of it. Did we do this last week? You know how to do the multiple roots in your calculators? I thought we did. If you don't have a root key where you can put in any number for the root, then you can take the power of the value to, this will be 1/4. Say 1/4 power. Y to the x be y to the 1/4, or y to the 1/3, y to the 1/2, or y to the 1/4. That works also if you don't have a root key, which I don't. So I have to do it the hard way. Okay, so 1.8 exponent minus 18. We're going to divide by 27. Right? That gives us 6.7 times 10 to the minus 20, and then take the 4th root of it. So I need to do 0.25 and then get my power key. So in this one, s is equal to 1.6 times 10 to the minus 5. And so let's outline those so we can separate them. This one will be 3 exponent 27 negative enter. And then we're going to divide by 4 and take the 3rd root. So 0.333. And this one is 9.3 times 10 to the minus 10. There we go. This one we just take the square root. And that's, I should have been able to do this with my head. 10 to the minus 14. There we go. 6.1 exponent minus 5. And take square root of that. So this s is equal to 7.8 times 10 to the minus 3. And the last one, 2 exponent 33. Divide by 27 and then take the 4th root of it. And this one is, let's see, only one significant peak. 3 times 10 to the minus 9. Yes. Okay, So now we want to find out which one is the most soluble, lowest solubility. So I'll look at the exponents first. Right? Which one has the smallest exponent? -9, -3, -14, -14. And there are no other -14s in there, so we don't have to go to the coefficient for a tiebreaker. So it's this one right here. That one's the least soluble. It took a lot of work, I know. But I thought it was worth tackling that one. All right. That was 11, 13. The molar solubility of barium carbonate molar solubility of barium carbonate in 0.1 molar barium chloride. 0.1 molar barium chloride is the solution. Now, it's not pure water. I think they're looking for the molar solubility there because they gave us the KSP. Okay, so here's what we've got going. We've got this barium again and carbonate. And if we set up our ice table, we find that initially we have no barium, but we do, we have no carbonate, but we do have barium, 0.1 molar. All right, so what's the change? Well, there's no carbonate, so it has to go that way. We're going to get some over here, plus S, and we're going to get plus S here. So it's 0.1 plus S here and S here for our equilibrium expression. Okay, so KSP is equal to 1.6 times 10 to the minus 9. And that's equal to just this one times that one. 0.1 plus S times S. That's going to give us a quadratic unless we assume that the solubility of barium chloride is very, very low. This S is going to be a small number, and it's going to be even smaller. We know it's going to be even smaller because some of this is already there, the common ion effect. So what we can do is say it's actually 0.1 S. We drop that S out. So now we can say that looks like a 5. We just need to divide this one by 0.1 or multiply it by 10. So S would be 1.6 times 10 to the minus 8. Now I went the wrong direction. Excuse me. Okay. I tried to skip a step. This should be S equals 1.6 times 10 to the minus 9. This is in the numerator, it has to be in the denominator over here, 0.1. Okay, divide by 0.1 should be, yeah, I was right, times 10 to the minus 8, right? If this is 10 to the minus 1, it's in the denominator, that means you added to that, it's 10 to the minus 8. Oh, okay. Right, E, none of these. I was looking for the answer and it wasn't there. So that's the molar solubility in 0.1 molar barium chloride, demonstrating the common ion effect. All right, 17. Which of the following solid salts is more soluble in 1 molar H plus than in pure water? Let's see. The comparison here is water versus 0.1 molar acid. Now we have to assume here that this acid is not hydrochloric acid, because that would mess up our silver. It has to be nitric. Okay, so which one would be more soluble? Well, the idea of increasing solubility with acidity has to do with, let's see, let's just take the first one, for instance, sodium chloride. Sodium chloride would become sodium plus chloride ion in solution. And for any solubility problem like this, you look at what effect does this have on these items over here. It doesn't have any effect on this because it's a solid, right? It only has surface area there. But here, everything's in solution. So what effect does hydrogen ion have? Well, acidity, the increase in acidity and its effect on solubility, its positive effect on solubility, has to do with the anion. The anion must be a strong base. If the anion is not a strong base, then the hydrogen ions will not react with it. And of course, they're not going to react with sodium because they're both cations, right? So what happens when you add that to this? Nothing. Chloride comes from hydrochloric acid, which is a strong acid, makes it a weak base, weak conjugate base. So this hydrogen will not react with that. What we're trying to do is react this with a strong base on this side and drive the reaction to the right. Since this is a very weak base, it has no impact on that one whatsoever. All right, so A, it has no influence. How about B? Calcium carbonate. What is it going to break up into? Well, calcium ions plus carbonate ions. Okay. Is carbonate a strong base? Yeah. What is it derived from? Well, it goes through 2 steps, actually. And then this one loses another proton, CO3 minus SH plus. These are both weak acids, so they produce very strong bases. And this is the strongest base of all. So it gobbles up hydrogen ions like there's no tomorrow and removes this one from the reaction. It goes to this one, then this one picks up another hydrogen and goes to that one. So what it's doing is Le Chatelier. It's removing this from the reaction mixture and driving the reaction to the right. So this will increase solubility with acid for that reason. There are 2 ways that you can get a compound to be more soluble. One is if it has a strong conjugate base in its makeup. And the other is if it doesn't, then you attack the cation with a complex ion. Those are the 2 ways you increase solubility. In this case, we're looking for the strong conjugate base, and it's the only one of that bunch, because the rest of them have chlorides or nitrates, and those are all weak bases. So we found our answer. B is the answer because carbonate is a strong conjugate base of a weak acid. That was the whole point of that question. Took me forever to describe it, though. How about this one? 19. You have a solution consisting of 0.1 molar chloride and 0.1 molar chromate. You add 0.1 molar silver nitrate dropwise to this solution. Given that the KSP for silver chromate is 10 to the minus 12 and for silver chloride is 10 to the minus 10, which of the following will precipitate first? Okay. Let's see. We've got these two reactions that are under consideration here. We have silver and chloride here, and we have, let me put it out here. We have silver chromate. Is it 3? 4. 4 with 2 of these. So that produces 2 silvers and chromate. Okay, in solution. I sort of got crunched up over there. So which of the following will precipitate first? The one that precipitates first is the one that is least soluble, has the least solubility. We're given the KSPs. We don't know the solubilities yet. So if this is, let's see, this is ICE. So if we're going to have S, we're going to have plus S here and plus S here. We're going to have 0.1 molar plus S and 0.1 molar plus S here. And on this side, the change is going to be plus 2S, and this one is plus S. You know what? I'm still barking up the wrong tree. Even though we have these concentrations, all we need to know is what is the solubility. Because until we add some silver to this, there's no common ion in there. When they start off at 0, 0, 0, 0. So this one, the KSP for silver is, if I can remember, 1.6 times 10 to the minus 10, I think, equals S squared. So the solubility is the square root of 1.6 times 10 to the minus 10. So this is 1.3 times 10 to the minus 5 molar solubility. And this one is 9 times 10 to the minus 12. 9 times 10 to the minus 12. And that's equal to this one squared, 2S squared times S. Right? Yeah. So this will be 4S cubed. So I need to divide 9, 10 to the minus 12, divide that by 4, and then take the cube root of it. This key right here. So this solubility is equal to 1.3 times 10 to the minus 4. There we go. That answers the question. The least soluble one is the one that's going to come out first. Silver chloride. Okay. Now you're thoroughly confused. I think I'm still flustered from CX. I should have left sleeping dogs alive. And just told him about it afterwards. That was 19. Got about a half hour left. See how far we can get. All right, 21. How many moles of calcium nitrate must be added to 1 liter of 0.182 molar Kf solution to begin precipitation of calcium fluoride? And we're given the KSP for calcium fluoride. Okay, I gave myself a hint there. At what calcium concentration does Q equals KSP? So what we're looking at is this solubility. Right here. And 2 fluorides. All right. And let's see, let's go ahead and put the KSP up here. 4 times 10 to the minus 11. And that's going to be equal to calcium and fluoride squared. Okay, so 0.182 molar Kf. So what's the molarity of F? Well, Kf is completely soluble, and it produces like that, like that. So this concentration is the same as that concentration. So we know what our starting concentration of fluoride is. Right? It's 0.182 molar. And of course, we got to zero that. So if we calculate, the question is how many moles of calcium nitrate must be added? Well, what we're dealing with is how many moles of calcium do we need? And there again, we have calcium nitrate. One for every mole of calcium nitrate, you get a mole of calcium ions. And everything is in 1 liter. So we can keep it molarity. And once we find the molarity answer, that is equal to the moles because we've only got 1 liter. And we have to assume that we're not adding a whole lot of this to change the volume. If we have to take that into account, then it will complicate the problem even further. Okay, so what would be the Q for this one? Right, at what Q? Actually, we don't even need that. If we say Q is equal to, if we actually, okay, Q equals, if we say at this point, the KSP and the Q are equal. And then we calculate what concentration of calcium ions would it take. I don't even need the ice table. Would it take for this expression to be true? Now we solve for calcium. And at that point, then the Q is equal to KSP. And anything above calcium concentration of that level is going to precipitate. Okay? Yeah. I mean, remember, if Q is greater than KSP, then you get a precipitation. So at this, where Q and KSP are equal, you're right on the edge. And all you need is just a little bit more of calcium. So at what concentration of calcium would we start to exceed the Q for the KSP? So now we just solve for that value. So we need to square 0.182 and then divide it into 4 times 10 to the minus 11. And that's 1.2 times 10 to the minus 9 molar, but we're in 1 liter, so that's equal to moles. 1.2 times 10 minus 9, which is D. Right. I was making this too hard. It's really much simpler than it looks. Okay, okay. Let's see. Oops, I didn't mean to do that. I just wanted to move it up a little bit. There we go. 23. Okay. Did it to me again, didn't it? Oh, you can't see that. That's okay. A solution of 0.01 molar in each of these 3 compounds. Let's put the salts up here with their K values first. Lead 2 nitrate. No, hydroxide, excuse me. Hydroxide. There. And its KSP is what? 1.4 times 10 to the minus 20. Go. Who's next? Manganese. Manganese 2 hydroxide. And 2 times 10 to the minus 13. And then zinc 2 hydroxide. And it's minus 16. Okay. The question is, each one of these is at 0.1 molar. In the same solution. Sodium hydroxide is added until the pH of the solution is 8.5. So which of the statements is true? Solid sodium hydroxide is added until the pH is 8.5. pH is 8.5. Okay, notice that when these things go into solution, they're in equilibrium with the cation and hydroxide, each one of them. Okay, so if we these are the only ones that are given at 0.1. So if it's 0.1 molar for this, this, or this, then if for every one of these, you get one of those. So the concentration of each one of these is 0.1 molar. Right? That's your initial concentration for each one of these guys. What we don't know is this one, right? It starts off at 0. So the reaction is going to go to the right. And am I barking up a wrong tree again? I hate when that happens. Okay. What we need to know is, what is this concentration over here? And pH tells us what it is. pH, what's pOH? Remember that one? 14 minus 8.5, which is 65.5. correct? So what's the OH concentration? Well, it's 10 to the minus 5.5. Right, we just take the anti-log of negative 5.5. There we go. And there's my key. 3.2 significant figures. 3.2 times 10 to the minus 6. Molar. Okay, so we know that the concentration here is, actually we don't need that. 3.2 times 10 to the minus 6. So in this case, what we want to do is calculate what is the Q for each one of these and compare it to their KSPs. And for the ones where the Q is greater than the KSP, they will precipitate. So for the first one, this one, the Q is equal to what? It's 0.1 molar. Actually, it's the same for all of them, isn't it? Q is the same for all of them because they all have the same concentrations. Then we compare it to each one of their Ks. So 3.2 times 10 to the minus 6 squared. So that's going to be the Q. I just need to square this value and multiply it by 0.1. 1 times 10 to the minus 12. Okay. So whose K is less than that Q? This one's less than that Q, right? So no precipitation there. Oh, excuse me. I'm reasoning wrong. The Q is bigger than this value. So it is bigger than that one. And what's bigger than all of them? That's why the calculation didn't work. There we go. Now I bet it'll work. Exponent 6, change the sign, square that. Yep, and then times 0.01. All right, 1.02 times 10 to the minus 13. Okay, so which one is Q bigger than? Q's bigger than this one. Q's not bigger than that one. Q's bigger than this one. Okay, so lead and zinc will precipitate. Let's see. Q is greater than KSP. Let me be complete. For lead and zinc. You didn't miss anything except my mistakes. We found that I had that value wrong. So once I did the calculation with the correct value, it works. All right, that was 23, 24. Somebody coming back. That's what. 4. All right. In the qualitative analysis scheme for metal ions, how are the analytical group 2 cations separated from the cations of 3 and 4? All right, you just need to look at the useful information, which will be available on the test. So we notice that these are color-coded. So group 2 is these guys. And where are they separated? Well, when you add hydrogen sulfide in acidic solution, you get those separated out. So acidic H2S will precipitate those out, which is C, as metal sulfides. One. Let's see. I found a problem in here the other day. 10-2. Where's 10-2? There it is. Notice that up in this group up here, the last two, it goes 10-3 plus and 10-4 plus. There's no 10-3 plus. There's 10-2 plus. That should be a 2 plus. This came straight out of your textbook, so that's an error in the textbook. It should be 10-2 plus in group 2. If you look at your periodic table at the possible charges, right? Just go down there. Remember where those are on the upper right hand corner of each of the boxes? And you look at 10. 10 is 2 plus, 4 plus. There are no 3 pluses in there. Okay. That's because, let's see, what group is 10 in? 10's in 5. For 10, it has 5s2 and 5p2 as its valence. So it can lose these two and make a 2 plus, or it can lose all 4 and make a 4 plus. Right? That's the way it works. So that was an error in the in this separation scheme. All right, that's 24. 15 minutes and counting. Let's see here. Which of the following solid salts, 25, should be more soluble in 1 molar ammonia than in water? 1 molar ammonia, more soluble in 1 molar ammonia than water. Okay, what do we have here? We've got sodium carbonate. Does ammonia, when we recognize that what we're trying to do here is form a complex ion. You don't form complex ions with the anion, you do it with the cation. So will this form a complex ion with sodium? No. How about potassium? Chloride? No. How about silver bromide? Ah, there you go. It forms a complex ion with silver. So silver bromide will become more soluble in 1 molar ammonia than in water. That's the only reason for this question, for you to recognize that fact. All right. Oh, another one. We should be able to knock this one out fast. The correct mathematical expression for finding the molar solubility of lead 2 chloride. Lead 2 chloride. All right, so we're going to have lead and chloride aqueous. So if this is S, then we're going to have 0, 0. We're going to add an S and add a 2S. So eventually, at equilibrium, we're going to have an S and we're going to have a 2S. And so KSP, KSP, based on that solubility, is just S and 2S squared. It's the same as the hydroxide, the 10-2 hydroxide. Right? It's 4S cubed. Yeah, 4s cubed. $30. I mean, 30 is looks like definition. Which of the following leads to the formation of precipitate? Q greater than KSP. If Q calculated is greater than KSP, you'll get a precipitate. So we can move to the next one. All right, 34. Let's see, is this one going to take some? Calculate the solubility of silver chromate in 0.049 silver nitrate solution. Okay, yeah, this one's fairly straightforward. So the solubility of silver chromate, oops. Runaway eraser. This is solid. Makes 2 silvers and 1 chromate in aqueous solution. Okay. So what's our initial concentration? Well, silver nitrate is at 0.049 molar, so right, for every one of these, you get one silver. So the silver concentration is 0.049 molar. Okay. And the change is going to go this way. We're going to add some here. And we're going to add 2 here. Right. So what we get is 0.049 plus 2s and then s. So KSP equals 9 times 10 minus 12, which is equal to this one squared times this one. Okay. If we square this one, we're going to expand a polynomial. So we're going to have to assume that this one is insignificant. So we get 0.049 squared times s is equal to this value. Right. So we take this one, we divide it by this one squared, and that's equal to our solubility. Well, okay, so that one, I want to square this one, 0.049 squared, and then divide it into that one. So I get S is equal to 3.2 significant figures, 7 times 10 to the minus 9 molar. Is that on that list? Yeah, C. Okay. And we don't have time to do the 5% rule. Just have to assume, since this value is so small to begin with, this one's going to be even smaller. Oops, 8 minutes. How much time is this one going to take? How many moles of calcium fluoride will dissolve in 3 liters of 0.089 molar sodium fluoride solution? I think we can do this one. Okay. Calcium fluoride is our solid. It's going to produce this ion plus two of these ions, right? And we've got a concentration of 0.089 molar fluoride already. Right? So if this is initial, then we're going to solubilize some of it because we don't have any calcium over here to start with. Right? So we're going to add the same number of calciums. We're going to add two fluorides. Okay, so we get an S and we get a 0.089 plus 2S. Yeah. Okay, so first we're going to calculate the solubility, and then we're going to have to apply the volume because the question asks for how many moles, not molar concentration, but how many moles. So if we have the KSP is equal to 4 times 10 to the minus 11. And that's equal to S, get this out of the way, times 0.089 plus 2S squared. We're going to assume that this 2S is very small. Otherwise, we've got a quadratic. So this is S, and this is just 0.089 squared. So if we take this one divided by that one squared, we should get the solubility. 4 exponent negative 11, and then 0.089 squared. Then divide it into this one. Yeah. So the solubility is 5.0 times 10 to the minus 9 molar. But if we multiply that times, this is moles per liter. How many liters? 3 liters. That cancels the liters, right? This is moles per liter. It cancels the liters. And we get 1.5 times 10 to the minus 8 moles of calcium fluoride were solubilized in that 3-liter solution. And that would be C. Okay. Oh, I still got 5 minutes. Let's see what the next one has to offer. We might be able to knock it out. Yeah, 37. 37. What's the best way to ensure complete precipitation of SNS from a saturated H2S solution? We want to precipitate this one from an H2S solution. Complete precipitation. If this is all you've got in solution, along with the 10, you've got 10, 2 plus in aqueous solution. What you want to do is you want to maximize that concentration to react with this one. So how do you do that? To get most of this into solution, you remove as many of these as you can. Right? If you suck those up with a strong base, then you're going to drive it over here and make lots of this in solution. So the way you do it is you add hydroxyl. Right? Strong base, hydroxyl works. And that will guarantee that you have plenty of these to react with those. And that means this concentration increases, the Q value increases way past the KSP, and you drop all of it out of solution. So the answer to that was D, add a strong base. I guess we can keep going till the guys get here. So let me see if I can tackle this one. 40. Gonna mess with some seawater. The concentration of magnesium in seawater is 0.052 molar. Magnesium 2 plus is 0.052, is it? Yeah, molar. Okay. At what pH will 99% of the magnesium be precipitated? That's hydroxide. Okay, so they're saying it's precipitated as hydroxide. That means this is the equation we're dealing with. Hydroxide. We want 99% of that. Right, so we want to remove 0.99 times that. Or 5.15. I'm going to keep a couple extra. Times 10 to the minus 2 molar. That's what we want to precipitate out. So initially, we have 5.15 times 10 to the minus 2 molar. And we want to know what's the concentration here that will precipitate that. Well, let's see. We need twice this many, don't we? Twice that many, right? Times 2. Times 2 equals 1.03 times 10 to the minus 1 molar hydroxide. ASP is 9 times 10 to the minus 12. 8.9. 8.9 times 10 to the minus 12. And that's equal to 5.15 times 10 to the minus 2. And OH squared. Now I can solve for OH. 8.9 exponent 12. 5.15 exponent 2. Divide that into it. And then take the square root. There. So the OH concentration needed is 1.31 times 10 to the minus 5. The POH is the negative log of that, which is 4.88, and the pH is 14. Is 9.1. There we go. Or 9.12. Yeah, I rounded it off. There you go. Well, I'm still waiting on the other folks. Guess we can keep going till they get here. $41. Okay. So we've got a solution containing 0.018 moles each of these halogen ions. 41. Let's see. Iodine, bromine, and chloride, correct? Yep. 1.5 times 10 to the minus 6. Let's be 1.5 times 10 to the minus 6. 16, excuse me. 16. 5 times 10 to the minus 13. And 1.6 times 10 to the minus 10. Okay, here's a place where we can compare the KSPs. Since these are identical, X, Y, X, Y, X, Y, this is the order that they will precipitate as you add silver to these solutions. So since they're all X, Y, X, Y, X, Y, you can compare their solubilities by the KSPs. So this one's going to be the least soluble, this is the most soluble, and this is more soluble, this is the most soluble. What that means is the order of precipitation is this one's going first, and it's going to use up all the silver it wants until it's gone, till this is all gone. Then this one's going to use up what's left, and if anything's left over, then this one gets some. Okay, so when the question says when the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver chloride precipitates out? All you have to do is precipitate out this much, then this much, and what's left over is your answer. Right? So what do we got going first? 200 milliliters of 0.24 molar. 200 milliliters of 0.24 molar silver nitrate. Right? Yep. Okay, so how much silver is that? Well, 200 times 0.24 would be millimoles. We can do that. So we're starting out with 0.24 equals 48 millimoles. 48 millimoles. Okay. How much of each of the others are we starting out with? 0.018 moles of each one. 0.018 moles, which is how many millimoles? 1, 2, 3, 18 millimoles. I like working with millimoles because you don't have to do with decimals so much. Okay, so the first one is going to take out 48 minus 18 equals 30, right? 30 millimoles of silver will be left over to go down here. Right? So then 30 minus 18 would be equal to 22. 22 millimoles of silver are left over, and they go down here. 22. So notice with 22 millimoles, we've got enough to take out. Should have enough to take out all of this. Did I do the calculation right? 48 minus 18. Let's see, that's 200 times 0.24. That's 48. Yeah, that's 48. So minus 18 of them are gone here. That's right. Then 18 is 1, 2. Oh. Correct. That's better. Much more better. There we go. So now, we don't have enough to use up all of the silver. I mean, all the chloride. We're only going to have this many millimoles of silver chloride. And the question asks for how many grams. So we got to convert that back to 0.012 moles so that we can convert it to grams of silver chloride. Right? Moles on the bottom, silver on the top. So we need silver chloride molar mass. Silver is 107.87. and chloride is 35.45. So that's 2, 112, 13, 112, 13, 143, 32. Times 0.012. 143. So I get, let's see, two significant figures, 1.7 grams of silver chloride. Yeah, that's B. Okay. All right. So I guess we're ready to go in the lab, and let me see how much we got left. 41, we're starting at 43. So I'm gonna have to come back with 43. 1, 2, 3, 4, 5, 6. I got 6 more to do. So I'll come back and do that after the lab. All right, number 43. When a mixture containing cations of analytical groups 1 through 3, okay, it's only got those from 1 through 3. That's it. It's treated with acidic H2S. And I assume they mean hydrogen chloride, hydrochloric acid. Otherwise, their answer doesn't make any sense. So we go to our chart, our corrected chart. Right. 1, 2, and 3. If it's treated with H2S, acidic S, HCl first drops out silver, mercury, and lead. But hydrogen sulfide in an acidic solution will also get, group 2. So groups 1 and 2 will come out of solution together under these circumstances. So 1 and 2 only. Group 3 will be left alone. All right. 43. Let's scroll down to the next one. 46. All right. So what we have here is the formation of a complex ion with some hypothetical metal with a 2+ charge. Right, so let's see, 46. So our hypothetical metal has a 2+ charge, and it's going to associate with ammonia, set up an equilibrium there, MnH3 with a 2+ charge, because ammonia is neutral, so the charge stays the same. Let's see, I think they do it like this. There we go. So the first K is 10 squared. Okay. Second one, we take this one. And we add another ammonia. Still with a 2+ charge. And the second K is 10 to the third. And then one more. So we have this one plus one more ammonia. So they're saying this hypothetical metal associates with 3 ammonias. And this one is 10 to the second power. All right. A 1 times 10 to the minus third mole sample of the metal as the nitrate is added to a 1 liter of 15 molar ammonia. What's the dominant species in this solution? As the question is asked, that extra information at the bottom doesn't matter. It only matters that you've added metal to ammonia. And we just want to know which one of these is the dominant species out of this. So when you add metal and ammonia, you go to this side by a factor of 100. But then this one picks up another ammonia by a factor of 1,000. And then this one picks up another ammonia by a factor of another 100. So the overall K is equal to 10 to the 7th. So a factor of 10 million takes this metal from here to here. This is the dominant species. You can reason it 2 different ways. It goes this way, and then as soon as it gets here, it's picked up and goes that way. And then as soon as it gets there, it picks up and goes that way because the K is so big. Or you can do overall and say, okay, with this EQ 10 to the 7th, it has to be that one. Because when you add all these together, that cancels out, that cancels. This one goes out, this one goes out, and you're left with 3 ammonias and the metal in equilibrium with this species. That's the dominant species. Okay. 47. Okay, what does the problem say? What is the concentration of nickel ion in a 0.045 molar nickel nitrate solution that is also 1 molar ammonia? So we're forming a complex ion, and we want to know how much of the nickel is not part of the complex ion, right? So the equation we're dealing with is the nickel and ammonia associated. Okay, 2 plus ion. How many nickels? I think there were 6, weren't there? Yes, 6 nickels, 6 ammonias makes this complex ion. Six. And what's the charge? Well, ammonia is neutral again, so the charge is the same. Okay. All right, so that's the equation. And when we first put them together, what's going to happen is the reaction is going to go to completion. At least that's the way we're going to treat it. In other words, how much nickel do we have? 0.045 molar. Nickel to nitrate. For every 1 nickel to nitrate, you get 1 nickel. So the concentration is the same, 0.045 molar. The ammonia is 1 molar. Okay, and of course you got nothing over here. So this is the, so that I don't get it confused with the ICE table, let's call it something else. Let's call it start and finish. Okay, so if we react them all together, we're going to use up, let's see, are we going to use up all of the nickel? Yes. We're going to use up all of the nickel. Well, finish is going to be 0. Right? So for every one of these, you get 6 of those. So 0.045 times 6 is, let's see, 30, 3 and 24, 27, and 2, 0.276. Okay? Excuse me, 0.270 is what we're going to lose here, minus 0.270. So the finishing point for ammonia is going to be 0, 3, and 2 from 9 is 7. There we go. Okay, so that's going to be the finishing part here. And we're also going to get 0, 1 to 1, right? 1 to 1, 0.045 molar here. Okay, so that's going to give us our starting point. Our this is a formation. We're using not KSP, but KF for this reaction. So we've got, I'm going to erase a little at a time. Now we're going to set up ice table. So the initial here is 0 and 0.730 molar, and this one's 0.045 molar. There we go. This is similar to our acid-base reactions where we had the stoichiometry first, then the equilibrium. We're doing the same thing here. Stoichiometry first, then equilibrium. So if this is the stoichiometric situation and that's 0, it has to move back this way some. Okay. So we're going to add some here. And for every one of these that we lose over here, we add 6 of these. Right? For every one of these lost, you lose 6. So they show up over here. Right, so we're going to have X here. We're going to have a 0.730 plus 6X. And then we're going to have a 0.045 minus X. Correct? Yes. Okay. So now we need to set up the constant formation constant for this ion. The value is 5.5 times 10 to the 8. Right? And the equation itself is nickel, ammonia, 6 of them, and 2 plus. And then in the denominator, we have nickel 2 plus ion, and we have ammonia to the 6th power. Okay? So now we have 5.5 times 10 to the 8 is equal to this value, 0.045 minus X divided by X for the nickel, right? And if we solve for X, we have our equilibrium value for X, for nickel concentration. That's what the problem asked for. And then 0.730 plus 6X. Okay. I think we're going to have to estimate 0.045. That X is going to be very small. Why? because this equilibrium constant pushes way to the right, way to the right. That means these X values are going to be very small, right? What's left over is not going to be very much. So we leave this X alone, and we remove the X from, remove the X from this one. We got to use the power. Let's try that again. 0.045, enter. 0.73 to the 6th power. Divide that into it, and then divide 5.5, 10 to the 8th. That. 5.4 times 10 to the minus 10. There we go. This is the part that I messed up on right here. So that would be the concentration of nickel, right? X equals the equilibrium concentration of nickel. Okay, number 50. All right, 50. What's the molar solubility of silver chloride in 1 molar ammonia? Okay, we've got two things going on here in the same reaction mixture. We're trying to solubilize silver chloride like this. And that. Let's go ahead and put the K up here. The KSP for silver chloride is 1.6 times 10 to the minus 10. Okay. And we also have going on here the formation of the complex ion. Two of those. And we form a complex ion here of silver and ammonia. There we go. Oops, my mistake. Here we go. I think that's right. And this one has a K of formation of 1.7 times 10 to the 7th. There we go. Okay, since both of these are going on at the same time, in order to determine the equilibrium status, we've got to combine the equations, right? And it looks like silver chloride will be on this side, yes. Then silver ions will go out. Ammonia will still be on this side, and the complex ion will be on that side with the chloride. Okay. Or I can just write the whole thing out and show you the cancellations later. So let's do that. So we've got, let's take the top one, silver chloride plus silver ion. I'm going to leave the, I better put it in. Could get confusing. Okay, and this is going to be in equilibrium with silver ion with plus chloride aqueous plus the complex ion. Aqueous. Okay. So notice we've got silver on both sides. So that has to go out. And we're left with the solid, the ammonia on the reactant side, the chloride, and the silver complex on the right-hand side. Okay, so what's the KEQ for this one? Let's see, let's put it over here. The KEQ for that reaction is KSP times KF. Right? Because we added these together, we multiply the equilibrium constants. So 1.6 times 10 to the minus 10 times 1.7 times 10 to the 7th equals, let me use my calculator for this one. 1.6 exponent minus 10 and 1.7 exponent 7 times 2.72 times 10 minus 3. I'm going to keep an extra digit here just to avoid rounding errors later. So this is the KEQ for that expression. So if we're going to assess the solubility of this compound, and we say the initial concentration of ammonia was what? 1 molar, wasn't it? Yeah, 1 molar. Initial concentration here is 1 molar. The initial concentration of chloride in this one is 0. Right? Because nothing's in solution yet. So what's the change? Well, the solubility of silver chloride is going to determine how much goes that way. Right? So we're going to get how much on this side? Well, for every one of these, how many chlorides do you get? Right? You get one of those, correct? And for every one of these, you get one of these. Okay? For every one of those, we had to lose some of this. We had to lose twice that much. All right. So at equilibrium, what we have is 1 minus 2s, s, and s. Okay, so now we can set up our equilibrium expression. I've used up a lot of room, but I'm going to try to squeeze it in here. So this value, let's see, is equal to chloride. Let's do it this way. Let's do the complex ion first. Right? And then we have the chloride. There we go. And then on this side, we have ammonia. Oops, not that. Ammonia to the 2nd power. Okay, so we can plug in values for these. Well, unknowns. We can plug in unknowns for this one. This one is S. This one is S. This one is 1 minus 2s. And this one is squared. Okay? So what is this equal to? Well, s times s is squared, correct? So it's s squared over 1.0 minus 2s squared. And remember, if this one's squared and that one's squared, it's the same as that one divided by that one, and the whole thing squared. It looks like this. So you have s, you have 1.0 minus 2s, and the whole thing is squared. And that is equal to 2.72 times 10 to the minus 3. Okay? So really all we need to do to get rid of the square factor is to take the square root of both sides. Okay? So if we do that, need my calculator for that one. The square root of this one is just this term. And the square root of that one is, let's see, s over 1 minus 2s is equal to square root of this. We just take the square root of everything. Is 5.22 times 10 to the minus 2. Then we need to multiply this one times that value and solve for s. All right. And in the interest of time, I'm going to give you the answer is 4.7 times 10 to the minus 2. Molar. That will give you the solubility of silver chloride. The solubility of silver chloride in 1 molar ammonia is 4.7 times 10 to the minus 2. The solubility of silver chloride in water would just be the square root of 1.6 times 10 to the minus 10. Is 1.3 times 10 minus 5. So that's in purely aqueous solution. So you've increased your solubility by 3 orders of magnitude, or 2.5 orders. All right, that was number 50. Okay, let's see, 52. Oops, there we go, 52. Yeah, 52. 52. All right, so what reactions are we dealing with here? For this system, 500 milliliters of 0.02 molar manganese 2 nitrate are mixed with 1 liter of 1 molar sodium oxalate. The oxalate ion, C2O4, is missing the charge. There should be a charge there. Should be a 2 minus charge. Let me make that note. 52 should be a 2 minus charge right there. There. Acts as a ligand. We didn't use that word before, but when these complex ions are formed, the polyatomic ion that attaches to the metal is called a ligand. This one has 2 ligands. Silver and ammonia. Ammonia, when it's completed, there are 2 ammonia ligands. That's what we mean by that. And they're governed by these 2 reactions. So the first one is step 1 with the oxalate ion, and these are aqueous MnC2O4, and they balance the charge. This is still aqueous. So the K, the first K here is 7.9 times 10 to the third. Okay. The second one actually works backwards. It says here's the complex ion, Mn, and then we have two of these. And the charge now is 2 minus. And this is aqueous. And this is in equilibrium with this one. Excuse me. This one here, plus another oxalate. And this K is 1.6 times 10 to the minus 2. One point 26. Excuse me. Try that again. 10 to the minus 2. There we go. Okay. When we put these in a solution, actually, this one needs to be reversed, because that one is going to pick up another oxalate. So it needs to be on this side, on the reactant side. This one needs to be flipped. Plus another oxalate is in equilibrium with the final complex ion, C2O4 twice and a 2 minus. Now, what's the K here? It's the inverse of that K. Right? So we just invert that number, 1.26. Excuse me. Try that again, 1.26 exponent to the minus 2, and then invert that number. 7.94 times 10 to the first power. Okay, so the overall reaction is what? The overall reaction is this one plus this one. Okay. Now, we need the overall reaction simply to tell us what the stoichiometry of the mixture is. We don't even need the overall K value. Why? Because the question asked is, what's the oxalate? Let's see, what is the Mn? What is this concentration here? Right. We just need to know what are these equilibrium or what are these equilibrium concentrations. But we can't get that unless we do the overall reaction. But the overall reaction doesn't need these values. It only needs the overall equation so that we can assess the concentrations of the various species that are going to go into this equation. Right, so we need to add these two together. Mn2 plus plus is that right? Yes, that's right. MnC2O4 And we got two of these. Okay, that's on the left-hand side. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and then on this side, we have this one, C2O4, aqueous, and we have MnC2O4, 2 minus. Okay, notice that we've got the same one here on both sides. So that's the overall equation. All right, now let's assess what did we start out with. Well, let's see. We had 500 milliliters of 0.02 molar manganese nitrate. So 1 mole of manganese nitrate makes 1 mole of manganese. So if we know the concentration of manganese nitrate, we know the concentration of manganese at the beginning. So the manganese concentration is going to be 500 milliliters, I believe, times 0.02 molar. Okay. So 0.02 times 500 is 10. Let's see, 3 significant figures, 10.0 millimoles of manganese 2 plus. All right. What are we starting out with the other? It's 1 molar, isn't it? Yes, 1 liter of 1 molar sodium oxalate. 1 oxalate for each sodium oxalate means 1 liter times 1 molar. All right, so we're starting off with 1.00 millimoles. Oh, excuse me, that's moles. All right, let's do it this way. Let me correct myself here. 500 milliliters is 0.5000 liters. So 0.02 times, well, it's 0.01. No. Yeah. 0.5 liters, enter, 0.02, 0.01, 0.0100 moles. Okay, and here we have 1 molar times 1 liter is 1 mole of oxalate. Okay, what is their concentration though? Right, their concentration is going to be this many moles divided by 1.5 liters. So 0.01 divided by 1.5 is 6.67 times 10 to the minus third. Molar manganese. How about oxalate? Well, 1 divided by 150, or 1.5, excuse me, 1.5 liters. So its concentration is going to be 6.67 times 10 to the minus 1 molar in oxalate. Okay, so now we have our values. And we can, now that we've assessed these values, this is, okay, We're going to keep that value. We're going to keep this value. And we're going to make room under this equation. Yeah, we only want to keep. Oh, my mistake. Yeah, we want to keep this equation. So I want MnC2O4 plus this one makes that one. All right. So now, initially we had some manganese, but all the manganese now is gone. So the manganese concentration is 0. What is the oxalate concentration? Well, with every manganese that disappears, we lose 2 oxalates. So if we're going from here, then we're going to lose right for every one of these that's gone, we lose 2 of those. Right, so this concentration will be 6.67 times 10 to the minus 1 minus 2 times 6.67 times 10 to the minus 3. Right, because we lost all our manganese. That's all of our manganese. Then we're going to lose 2 of those from that side. So this concentration will be 6.53 times 10 to the minus 1. Molar. Okay, so we got this one. And now we need this one. So how do we know that one? Well, that one's going to be the same as all of this that we lost. So we lost all of this one. It became that one. Right, so this concentration is going to be 6.67 times 10 to the minus 3 molar, because all the manganese is gone. It has to show up over here. And it started here, so it went to there. And this one is 6.53 times 10 to the minus 1 molar. Okay? Now we can write our expression equal to that K. Right? So 7.94 times 10 to the 1 equals this value, right? That value in the numerator. And in the denominator, we have this one. Let's call this one X. Okay? We have X. And then 6.53 times 10 to the minus 1. So we solve for X. Bring the X over here, put that one over in the denominator. And we should have our equilibrium concentration for the single oxalate of manganese. So I get 1.3 times 10 to the minus 4 molar. Okay. Now it's 52. I think we got one more. And that's 53. Yes, 53. All right. What's the molar solubility of lead-2 chromate in 0.055 molar sodium thiosulfate? Okay, lead-2 chromate. So we're looking at solubility, chromate, that's it, lead-2 chromate. And it's going to produce lead-2 plus in aqueous solution and chromate in aqueous solution. Okay, the other reaction that's taking place is the formation of a complex ion with this lead. And it's associating itself with thiosulfate. So thiosulfate should be 2 minus. Okay. Let's see, how many of those are we going to need? 3. Okay. So we get this complex ion. And that means 4 minus, I do believe. And the Kf, let's see, the K SP for this one is 2 times 10 to the minus 16. And the Kf for this one is 2.2 times 10 to the 6th. Here we go. Okay, when we combine these equations, when we combine these equations, because all of this is happening at the same time in the same solution. So we need a combined equation. So we've got lead 2 plus plus 3S2O3 2 minus. And I believe, right, we leave the solid out of it. Molar solubility, okay. Yeah, we could put it in there. Yeah, why don't we? There's the solid, because it's in there too. That's 3, and then over here we get lead 2 plus and chromate and the complex ion. Here we go. So notice that this one goes out on both sides of the equation, and the overall is KSP times KF. So the overall equilibrium constant for this one is 2 times 10 to the minus 16 and then 2.6 to the 6th power. So I get 5.2. So the KEQ here is equal to 5.2 times 10 to the minus 10. All right. So now what are we given? Well, let's see. What's the question? What's the molar solubility? If the lead-2 chromate is 0.55 molar sodium sulfate. So this concentration here is 0.055 molar. We know that. And at the beginning, there's nothing here and nothing there, right? If we make this initial, then what's the change? Well, it's got to go that way. So we're going to give up how much of this? Well, for every one of these, we have to give up 3 of those, right? If it's going that direction, this is minus 3s for solubility, right? Minus 3s. And then one of these is going to show up over here, right? Because for every one of those, you get one of these, plus you get one of those. So we get a plus S here and a plus S there, right? So at equilibrium, we get 0.055 molar minus 3s, and here we get S, here we get S. Okay? So now we need to set up our KEQ. So let me see. I'm going to start it up here, and I'll probably have to erase some to get to the bottom. So the KEQ is 5.2 times 10 to the minus 10 is equal to what? This one to the 1st power times that one to the 1st power. Let's just put in the values. So that's S times S, and then divided by this one to the 3rd power. There we go. All right, so I'm going to have to erase this to make room. Okay, so is S going to be a lot smaller than 0.055? Right? Are we going to produce that much? Well, the only way to solve this without using polynomial solutions or an iteration, that is successive approximations, is to say that this is equal to, approximately equal to S squared, right, divided by 0.055 to the 3rd power. So if we take this one, cube that one times this one, let's see what we get. 0.055, and we're going to cube it. So I said 3 there. And then that one times this one, 5.2 exponent 10 times 10 times. So that gives us 8.65 times 10 to the minus 14 is equal to S squared. So we just take the square root of both sides. Yep, take square root. So that's 2.9 times 10 to the minus 7 molar solubility. Here it is. 2.2 This is 4.4. This is 4.4. And this .055, enter 3 there, 4.4 exponent. That's 10 times 7.32. Okay, so that one is right, and I was wrong. Square root 2.7. There you go. 2.7 times 10 minus 7. This is the correct answer.